Okay, let's begin.
Yeah. And also email me after this could have already changed my law. He said that he could have had.
I have the midterms to give back, so we'll end like 5 minutes early and I'll hand those out at the end because I don't want you to be reading them instead of paying attention.
So I really won't care. So I just want to ask you.
Some of that is what we were doing last time. Some new ideas that we got. Okay, so we had some general counting principles. So we have something called the multiplication rule. And that was saying that if you have multiple stages in an experiment, then you have stage 1, stage 2, etc. to stage n. Right? There are n number of ways that this can happen. N1, N2, N3, all the way to Nn. Then the total number of outcomes, total number of outcomes is the multiplication of all of these numbers. The multiplication rule. And if all the n I are the same, this just comes out to just n raised to the nth power. We looked at both of those. Then we looked at some other things. We looked at tuples. So now we also looked at counting in situations where order matters. And we looked at the permutation, P of n comma m. This is going to be basically n factorial over n minus m factorial. We're looking at the calculators. And this was the number of ways to choose m objects from n objects in order with no repetition. So that was an important number that we learned. If repetition is allowed, it devolves into this case. Right? So the repetition case is just the multiplication. So I'm just making note of that. Covers the repetition allowed. So that's what we should be aware of. So P and M does not allow repetition, but it does matter the order that you are doing things in. And so, because that one was when we're counting tuples, tuples have some inherent order. There's a first element, a second element, a third element, so on and so forth. And there are other situations that we can count where order does not matter. And this was where we introduced the number called the combination, Cn. And that was basically n factorial over m factorial times n minus n. And this was the number of ways to choose m objects from n objects, ignoring it's also called, quote unquote, N choose M, or N choose R, if your calculator use is R. And another way to write that notation is this. For that one, it's pretty much yeah. So we have a bunch of situations, some general counting principles in terms of stages of an experiment. The multiplication rule. When there are different numbers potentially for each stage. If you have the same number of outcomes for each stage, so for example, like that phone numbers example I gave you, we can use this one, repetition is allowed. If you want to choose M things, put them in a certain order, not repeating anything, we use what's called the permutation. It's so called because of PNN. PNN equals N factorial. This is number of ways to arrange N objects. So order matters over here for all of these, and order does not matter over here. These are some general counting principles. And basically, a situation is going to be described to you, and you kind of have to figure out which of these are you going to look at it as. We did a bunch of examples where we're just applying the multiplication rule in different situations. I think today we're going to apply some of these guys over here. And yeah, it depends on the situation. So another common example, I'm not sure if I wrote this down, but you'll probably see it in the homework or in your textbooks because it's a very common thing. You can have situations where you're choosing out of groups of people, for example. Let's say you have, okay, there are 20 people in this room. I need 5 of them to come over here and help me move this big piece of furniture over here. I don't care who you pick, just pick 5 random people and you let them come help me. How many ways could you do that? How many possible groups of 5 people could leave that room and be selected? In that case, you would actually use this. Because it doesn't matter order. You're not like identifying anyone. No one's the first person or the second person. Hey, there are 20 people in a room. Just choose a random 5 out of the room and let's move on. Versus if I had 20 people in a room and I know, oh, I have a committee that I want to create with 5 distinct positions. There's a president, and there's a vice president, and there's a treasurer, and then there's the receptionist, and then there's blah. Right? There's an inherent order there. There's a hierarchy, and so you would use this instead. So it all depends on the situation, right? You can be choosing from groups of people in both situations, but if there's an inherent order versus not, will tell you who you want to kind of pick, because it will make a difference in those cases. Okay, so that's just a summary and just some clarifications there. Make sure you are aware of all that. Now we already started some examples. We're going to finish those on the handout. And I'm not sure how much time we'll have for the actual probabilities, actually. I guess we'll start to actually do with probability today. So back to counting examples. You did up to 6, I'm pretty sure. Okay, so 7. There should be 9. I don't know why the 8 is missing from that. There are 9 problems. Okay, so hope you're familiar with cards. I put a small little description here because we're going to talk about cards in this situation. There are 13 kinds of cards. You have the ace, the 2, the 3, the 4, the 5, all the way up to 10. Then you have the jack, the queen, the king. The ace can be used as a 1 or an 11. Depends on the game you're playing. There are 4 suits. You can have hearts, spades, clubs, or diamonds. So you can have something like an ace, where there's an A, and you can have an ace of diamonds. And you can look like that. So this is ace of diamonds. Or you can have the ace of, looks like a little clover. It's called the ace of clubs. You can have an ace of spades. Spade is just a shovel. the way a heart's gonna look. Okay, so we have things like this on the playing cards, and this will be, you'd have 4 kinds of cards like this for each kind of member. So you'd have it for the A's, then 2s, then 3s, then 4s, and 5s, all the 10s, the Jack, the Queen, the King. Okay. So ultimately, if you're keeping count, how many cards does that make?
52.
52, 13 times 4. Okay, so there are 52 total cards in a deck, not counting the Joker. And it depends on the game, the Joker might be in play, but usually it's not. Okay. Oh, so that is actually a part of this. This was just my introduction. Okay, so let's actually look at how many ways can we get certain poker hands. So let's say you're playing 5-card poker. We want to count the number of possible hands that you could get. Okay. So the cards, you have 52 of them, kind of look like this with different numbers written on them. And yeah, a dealer is someone who just shuffles the cards and deals out cards to everybody. He doesn't look at them. Often you have them face down. So A. How many possible 5-card hands are there? That's the first question, yeah. How many? Someone's shuffling a deck, they give you 5 random cards. How many possible ways could that situation turn out? Yeah.
Well, order matters here, so does repetition, right?
Ah, well, let's think about that. Let's say I gave you an ace of spades and a jack of clubs, versus I gave you a jack of clubs and an ace of spades. Does your hand change? So order does not matter. So, but that's good. That's what you're going to start thinking about. You're going to note here, order does not matter. Right? It doesn't matter what order the dealer deals out the cards to you. In fact, they're going to be face down. You're not even going to know really what he gave you first versus second. It's not going to matter. It's just you lift up your hands, you have these 5 cards. So order does not matter. That automatically puts you in a certain mindset. That means you're not going to be looking at permutations at all now, right? So it's probably going to be maybe between the multiplication rule and the other guy. What are you thinking here? Yeah.
Multiplication rule.
How would you do that?
You start with 52 cards, and then your next possibility would be 51 cards, and then 50 cards.
Why 51?
Because if you're giving away a card, aren't they dealing out 5 cards?
Yes.
So if you're dealing out a card...
No, he's dealing all 5 to you. Like you're getting all 5.
Oh, okay.
Right. So he just has a 52 card deck, he gives you 5 random cards. Like how, when you lift the cards up, how many possibilities are there? Yeah.
Would you just use a combination formula?
What formula would you use?
54 factorial over 5 factorial over...
Well, just tell me the combination form. What are you thinking?
Like the number, like the total number of sets you have over... I've been in a different format, but it's n factorial over x factorial over n minus x factorial.
Yeah, but there's a nice way to write it, right? With a big C. C 52 5. Or you can write it as 52 and a 5 on the bottom. Or you can write it as 52 big C then a 5. In other words, how many cards you have is 52 choose 5. That is literally 52 choose 5 random ones. I don't care what order. I.e. there are 52 choose 5 possible cards. Because order doesn't matter. I just have a set of 52 things and I want to pick 5 random things from that 52 things. Not necessarily in order. That means I'm thinking combinations. I have a group of 52 things, I want to get 5 of them together. How much is that, by the way? So this is 52, 5? 2 million?
560.
That's how many possible 5-card poker hands there are. Yeah, just 5 cards, but a lot of possibilities can happen with those 5 cards. It's possible for a bunch of people to play poker every day their whole life and never have to play the same game twice. That's a lot of possibilities. Okay, I defined something called a full house. Full house. So we say you have a full house if you have 2 cards of the same kind. And another 3 cards. That's it. It pairs up in 2 and 3. Thought of as the 2 being the parents and the 3 being the children. It's called a full house. 3 kids. I don't know why you call it a full house, but that's what it's called. Now, of all the possible card hands, there are 2,598,960 of them. How many are full houses? So how many of these card hands, how many of these is actually a full house? So, number of full houses. Go. What do you think? How are we going to figure that out? Yeah?
You can use a combination.
Sure.
Well, there's 4 different suits that you can have at the same time.
Yeah, so dissect it for me. How are
So
we
is it
gonna-
13 like choose twos or see 13 two for one or?
But why is 13 choose 2? Explain your reason.
I was gonna say because you similar. It has to be within the same suit, 2 cards.
Well, maybe let's draw out the situation and see what we want. Okay, so here are the 5 cards. Not necessarily in order. I'm just thinking of these as stages or something. So here, I know these 2. Let's make sure that they're the same kind. And these 3 here are the same kind. Of course, different from the first. Okay. So these could be 2 hearts, and these could be 3 diamonds. Right, so something like that. You get 2 hearts and 3 diamonds, that's a full house. So you can get 2 clubs and 3 spades, that's a full house. Right, so now how would you actually do that? Yeah.
Well, isn't a full house the same number? It's not the same. Yeah, it's not the same suit. It's the same number. Maybe like 2 2 3 3 3.
Sorry. 10 kinds. So it's like you have 2 2s and then 3 kings.
Yeah, me too.
That's gonna matter. It's just one possible example. How would you figure out what do you yeah?
Would you write the possibility of getting the first 2 cards and then the last 3 cards together?
Okay, let's deal with the first 2 cards. So number of ways to choose the parents. How many ways is that? So let's focus on the first 2 cards. How many ways can we create those 2?
4.
Yeah. How do you know I want the same thing? The same. Like how many possible numbers are there? Right, like we have, what do we have? We have the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, right? And each of these, they have 4 in place. So this is hearts, clubs, spades, diamond. This has a hearts, clubs, spades, diamonds, etc. So how many of these possibilities are there? There are 13 of them. So how do I choose the parents? Well, it means I would have to choose one of these, right? First I have to pick who is going to be in the first position. Is it going to be which one of these guys? So I would say it's 13, you choose one. This way you times 13. Okay, so that's me going through these 13 and I select someone that I'm going to put in here, right? So let's say, okay, 6 is chosen. Boom. Now that situation splits up into how many possibilities? There are 4 possibilities for that one, right? So it could be the hearts, or the spades, or the diamonds, or the clubs. So once I choose at random one of these guys, now out in there I would have how many choices that can I make from this? How many of them do I want? I want 2 of them. There are 2 slots I need to fill. How many, what's the total number of choices I have to choose from? 4. It's 4. So 4, choose 2. So first I'm going to pick what number I want. Once I pick the number, there are 4 possibilities. I'm going to pick 2 of them at random. How do I do that? Well, out of 4 possibilities, I just make a choice of any 2. What I just applied here was the multiplication. Here, what I did was I picked the kind. Here, I picked the suit. And here, I'm applying the multiplication. So here's how I'm thinking about it. I'm breaking up picking the cards into stages. First, I need to pick what number I want on it. Then I need to pick what suit it's going to have. So I think of stage 1 as picking one of these guys. Stage 2 as picking 2 random ones out of the number that I picked. And then multiplication rule says that's going to be how I'm going to do that. So that's how many ways you can pick the parents. How many ways can I pick the children? I guess I'll just. Kind of use the same principle that I mentioned. Yeah.
12 over 1, 4.
12, choose 1. Why?
Because you already used 1
Right, because I used the kind, I already picked the 6. So now, for the children, I'm going to have to pick someone else. Now there are 12 possibilities. I'm not choosing anything in any particular order, so out of that 12, just pick any random one. That's 12, choose 1. That's actually, in fact, equal to 12 itself. I had 12 choices to pick, 12, choose 1. Now, once I pick one of those choices, say I picked, so here are the parents, and then I can throw in, let's say at random I pick the jack for the children. Now there are going to be 4 possibilities there. Yeah.
Wouldn't it be like 12.5, choose 1, because there's still like 2 6s left?
No. Why would it be 5? No, you're focusing focus on the stage. You don't care how many there are in the group. You're focused on picking the group itself.
Okay.
I'm focused on picking one of the 6s. Then I worry about how many there actually are, right? So focus on picking a 6. Okay, how many are there? There are 4 of them. I pick 2. Okay. Now focus on picking one of the other guys. Random. I pick a jack. Okay. Now focus on picking how many of those? 3. I need 3 random ones out of that. So I can pick, say, these 3. How many ways can I choose the 3 out of the 4?
4 choose.
So 4 choose 3. So here I would pick one of the remaining kinds, because it's not going to overlap with that guy. Remaining kinds. And then I pick 3 of that kind. And then, how many total ways to do that? Well, multiplication rule says I'm going to multiply them together. So that's how many ways you can choose the parents, and this is how many ways you can choose the children. How many ways to choose a full house? Yeah?
Did you add these together or no? You multiply?
You treat it as like 2 stages of picking.
Treat it as 2 stages again. Now you look at the full house as both stages combined, choosing parents and then choosing the children. And you're going to just multiply all these numbers together. That's 13 choose 1, 4 choose 2. Then I'm going to multiply by 12 choose 1, 4 choose 3. Right, I don't want you to get into the, I guess I should add them, or I guess don't guess. Like there has to be a there has to be a scheme that you're thinking in terms of. The multiplication rule is such a scheme. So if you want to count something, you have to think. Am I thinking of it in stages? Does order matter? Does order not matter? Yeah.
I'm thinking of this weirdly, but like, would the number be different for like choices if you picked the kids before you picked the parents?
No, because that would just be like me choosing the children before the kids.
Yeah, but I'm saying like if you were choosing the children first, then would you have 13 choices, not 12?
You also have 2 choices.
Those were two.
Yes,
Okay.
so these 2 would swap, but it's a multiplication, so it's not going to matter. Yeah, the order is not going to matter. So yeah, it comes down to I have to choose 2 of a kind and 3 of a kind. Just think in stages. What does it mean to pick 2 of a kind? Well, first I have to pick the kind, then pick 2 people out of that group. Then I have to pick one of the remaining kinds, pick 3 out of that group. That's how I get the parents and the children. So how many ways can that be done in total? Well, if I think of that as 2 stages, choosing the parents and choosing the children, I just multiply them by the multiplication rule, and that will give me the total. What is the total, by the way?
3,000 total,
3,744. Yeah, that sounds about right. So that's the answer. I mean, kind of went out of order here. So this was the first part of the problem. Moved over here to the second part of the problem, and this is the third part of the problem. That's the final answer. There are 3,744 possible ways to get a full house. Now, based on what I said 2 classes ago about probability, what is the probability of getting a full house? Yeah,
It's all the possible ways you can get that, and then divided by
total possibilities, which is, boom. What are the chances you're going to get a full house if someone deals you 5 cards at random? That number divided by that number, what is that? Huh?
Yeah, I got
hold on. BTW. The chances of getting a full house. When dealt 5 cards at random. It's going to be equal to the 3, 7, 4, 4 divided by that thing I just erased. That's 2. Was it 980? 2, 5, 9,
8, 960.
960?
Yep.
That, which is, huh?
0.14%. 0.14.
Is that in a percentage?
0.14%.
Yeah.
0.14%. Which that base that's like if I were to write it as not a decimal, it's that. Which means on average, if you were to play a game of poker 10,000 times, 14 of those times roughly you would get a full house. You know how long it's going to take you to play 10,000 games? You can play a bunch of poker games with your friends for like entire semester, 2 semesters. Never get a full house. It's possible, right? It's not, the chances of that is not, they're not very good. And the numbers are one thing, but that's where the strategy in the game of poker comes from, right? So when you see something on the table and you know what it needs to beat it, and you know the probability that the other guy has a hand better than your hand, so you'll be able to call his bluff with more confidence that, yeah, there's no way this guy, I mean, the chances of him having something better than this, nah. Okay. So yeah, so you can walk into there knowing that, you know what, chances that I'm playing 5-card poker with a bunch of people here, you know, the chances that any one of these people got a full house just now with this turn of the game, 0.14%. So if I'm anything better than a full house, I mean, I'm 90-something% chance that I could win this hand, and no one's going to outmatch me. Well, it's a little more complicated than that. You need to know the percentages of the other ones. But yeah, that's basically it. So that was a tough example. That is number 7, obviously. But yeah, that many stages in that. Problem 8, and I'll probably ask you about some other kind of poker hands. Let's look at problem 8. You label 10 balls, you 1 through 10, you put them in a box, you shake it up, pick 5 of them randomly. After each pick, you do not replace the ball before picking again. So this is called without replacement. How many possible scenarios are there of this kind? 1, the second of the 5 numbers drawn is an 8. So you have these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you number them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Put in a box. Shake. Pick. Five at random without replacement. So now let's do A. How many possibilities are there for you to actually choose so that the second of the 5 numbers is an 8? What do you think? Yeah.
So if you use multiplication rule here, do you do like 10 options?
Okay, so we are choosing 5.
Yeah.
So I'd actually probably think of it as 5 options.
Yeah.
So here's my first choice, second choice, third choice, fourth choice, fifth choice. Okay? Alright, so what do we want here?
So 10 for the first one, and 10 for that.
Would it actually be 9 options because you know the second one has to be 8?
Right, so you are going to fill in what you know first. Now we know that the second one is an 8. We know that this is an 8. So an 8, as far as we're concerned, it's already chosen. It is designated as the second spot. Yeah.
For the multiplication rule, does that make it a 1 as far as leaving it out for students?
Yes, technically what I should have is 8 in quotations, but there is actually one choice. Yeah, that's actually right. When you want to multiply across. So there's only one choice for the second situation, right? It has to be an 8. So what can the first choice be? Well, there are 9 choices. For the third, well, 8 choices. And then 7 choices. Right, because you're not, this is because of the without replacement. So once you pick something, you can't pick it again. And then 6 choices. So the multiplication rule says 9 times 8 times 7 times 6. Okay. Now, that, what is that?
3044.
3044?
24.
So that's how many possible situations that could happen with you choosing an 8 in the second place. Yeah.
You should do 9 pick 4. And PR 4.
It turns out being equivalent to 9 choose 4. Yes. This is actually in fact this is in fact P94, which suggests there's another way to think about the problem. Like, what would you have to think about it here?
Yeah.
So, yeah.
Would it be kind of like, we technically have 5 options, but because we
Yeah,
know
so
one-
it's like one option given. So
So therefore we have 4.
so only 4 options left out of 9 possible options, right? So originally you had 10 possible options and you had 5 that you wanted to pick. One was chosen for you, which means now you have 4 choices left to make, and out of 9 possible choices. And now the important part is in order. Right? The number on the balls is an inherent order. There's a first one that I have to pick, and the second, and the third, and the fourth that I have to pick. So you can also think of it in terms of permutations. Which isn't strange. Remember, we actually figured out the formula for the permutations using the multiplication rule. So there are times when you can actually think of it as both. So yeah, you could look at this as, oh, well, that one choice has already been made for me. I just have to pick the other 4 in a certain order, right? So that's just 9 choose 4. Let's look at the next one. Okay, so B, the second of the 5. Is larger than the first. Okay. How many ways can you select these 5 in such a way that the second number is going to be bigger than the first number? And I don't really care what happens otherwise. Yeah.
Yeah, it's the stages.
Okay, what's the stage? 1, 2, 3, 4, 5. Any restrictions here?
The first number.
How many possibilities here?
The first one has to be 9 because you can't have 10 in the first
nothing I can do in the first one.
Yeah, well, doesn't it depend on what you're picking? Like if I pick the 10 here, then yeah, any of the other 9 can go here. But what if there's a 5 that shows up in this location? Then there are only 4 choices left for here.
So you pick your second one first.
Okay, so you'd focus on the second. And what are the options for the second?
There's still 9 options, but you can't pick the one. So
There's still 9. The 1 definitely is not going to be in there, so there are 9 possible options, right? So this could be a 2, it could be a 3, it could be a 4, could be a 5, could be a 6, could be a 7, could be an 8. Let's start higher. Now we don't have to do this, but it's nice to actually draw pictures so you can kind of think through the process. 3, 4, 5, 6. The second number could be a 2, or a 3, or a 4, or a 5, or a 6, or a 7, or an 8, or a 9, or a 10. Which already tells you what are we going to be doing here. We're going to be adding these because it's going to be one of these possibilities. Okay, so if the 2 shows up in the first position, how many choices can happen? There's only 1 choice, so here these should be in quotes. I'm not saying the number of choices here, I'm saying the actual thing that's in this position. Now, if there's a 2 in this position, there's only 1 choice that I have for this position. How many choices do I have here? 8, 7, 6, right? There are 8 left, and then there'll be 7 left there, and there'll be 6 left. If I have 3 over here, how many choices do I have here? Now there are 2. I could pick either the 1 in quotations or the 2 in quotations. And how many would I have here? It's again 8, 7, 6. In fact, that's going to be the pattern, because once I've passed these 2 stages, there will be 8 guys left, and I don't care what order those guys are chosen. So. Okay, but here, these guys are going to start to bump up, right? What about 10? Then any 9 could show up here. And so what we have, it's going to be, how many possible ways this can happen? Well, it's going to happen in 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 times 8 times 7 times 6. And that's the sum of the first 9 terms. We actually have a formula for that. That's 9 times 9 plus 1 all over 2. I showed you guys that when I was deriving the amortization formula. You know, baby Gauss figured it out with adding up 1,000 numbers. So times 8 times 7 times 6. Saturday. Ten times 9 times 4 times 7 times 6.
15,120.
Hunting's rough. It'll take some getting used to, so don't worry. You have homework on it, so that'll give you some more practice. And now I will do the test guys, and I will see you guys on the.